Welcome learners. I am Dr. T. Gangaram, lecturer in statistics, SVA Government College, Srikalahasti. In this video lecture, we will discuss simulation of continuous random variables application in pharmaceutical sciences. Why should pharmacy students learn simulation? Imagine a practical situation for a pharmaceutical company. If 10 million paracetamol tablets and 5 million antibiotic capsules, 2 million vaccine doses are produced. This company manufactures this amount of tablets. Can the company test every single medicine before selling it? Impossible. It is impossible and it is meaningless also, because every tablet, before going to a particular use, it must be tested and it must be confirmed the dosage and the particulars of that tablet composition. So the simulation saves time, money, human risk, and improves quality. Real life applications of simulation in pharmaceutical sciences are: it allows pharmaceutical companies to perform millions of virtual experiments. These are not real experiments, these are virtual experiments using random numbers and probability techniques. Before real world testing, the pharmaceutical companies perform virtual experiments. The major applications are tablet dissolution, that is, predict dissolution time, ensure quality standards, drug absorption, estimate blood concentration, optimize dosage schedule, and clinical trials, predict treatment success and estimate the side effects of the drug, and shelf life prediction, estimate expiry period, and study drug degradation. All these five major applications are by using simulation they can conduct: tablet manufacturing, computer simulation, quality prediction, safe medicines is the goal of simulation of random numbers. The key idea is, instead of experimenting on millions of tablets or patients, we just experiment on millions of computer generated observations. This process is called simulation. If a pharmaceutical company manufacture 1 crore tablets today, can it test every tablet before selling it? Absolutely no. So, how do scientists ensure quality without testing every tablet? Simulation creates millions of virtual tablets. It creates virtual tablets and it predicts their behavior using probability distributions. Think, suppose a paracetamol company wants to simulate a resolution time of 10 million tablets. The first question is, how does a computer generate millions of observations? The answer is simple. Every simulation begins with uniform random numbers. Remember, random numbers, uniform random numbers. These numbers lies between 0 to 1. Between 0 to 1. U is the uniform random number. The range of uniform random numbers are 0 to 1. Computers cannot directly generate exponential, normal, or gamma random variables. It first generates binary, that is 0 and 1 uniform random numbers, and then transform them into the required distribution. The first task is to generate uniform random number. Can a computer directly generate an experimental exponential random variable? Statistical software R, Python, SPSS, SAS, MATLAB, all these computer background softwares generate numbers between 0 to 1, and everything else is obtained by transforming these numbers. Here, uniform random numbers the starting point of every simulation. Here the pharmacy scenario is a company manufactures 10 million tablets in a day. For quality control, one tablet is selected completely at random. There is equal chance for every tablet to be included in the sample, that is completely random. Every tablet has equal chance of being selected. The idea of equal chance is called a uniform random number. Wherever chance enters, our probability theory enters uniform random variable. Every value is equally likely. No value is preferred out of other. Random numbers lies between 0 less than or equal to u less than or equal to 1. Here the uniform distribution is denoted by capital U. Uniform 0 and 1, all values are equally likely. The range is between 0 to 1 only. Here the key observation is every simulation algorithm begins by generating an uniform random number and then transform these random variables into the required probability distributions. Suppose the random numbers are 0.23, 0.47, 0.81 and 0.94. Here every number is between 0 to 1 and has the same chance of being generated. That is why this distribution is called uniform distribution. Here the random number generated randomly between 0 to 1. Uniform means equal chance. Every simulation starts here because computers can easily generate uniformly distributed random numbers. The next challenge is to convert these into the required distributions, particularly if time involves exponential, normal, gamma, or other distributions. Why does statisticians always use uniform? Why not uniform 0 to 100? Uniform 1, 0 to 1. Why not uniform 0 to 100 or 0 between 5 to 10? Because if computer can generate random numbers, why do statisticians always choose numbers between 0 and 1? The reason one is the probability always measured on the scale 0 to 1. Probability of an event is lies between 0 to 1, and the reason 2 is the cumulative distribution function, or simply distribution function of a random variable also satisfies 0 less than or equal to f of x less than or equal to 1, where capital F of x is equal to probability of x less than or equal to capital X less than or equal to small x. Therefore, both uniform random numbers and cumulative distribution functions lie on the same probability scale. Here, uniform 0 to 1, this is the probability scale of uniform random variable, probability of an event, and the CDF. The key idea is, since both the uniform random variable and CDF takes values between 0 and 1, we can simply write capital F of x is equal to u. This simple equation is the foundation for the inverse transform method. From uniform random numbers to any distribution, the big question is, first we know that u is distributed uniformly between 0 and 1, and every cumulative distribution function satisfies this inequality 0 to 1. Since both lie on the same probability scale, can we relate them? Yes. We simply equate them. F of x is equal to u, where f of x is the CDF of the required distribution and u is the uniform random numbers. Since the range is equal, we can equate them both. The computer generates a value of u. We then find the corresponding value of x. Here the key observation is a uniform random numbers is converted into a random observation by solving the equation f of x is equal to u. This idea is called the inverse transform method. Let us start with a uniform random number. Suppose the computer generates a random number u is equal to 0.73. This is the number randomly selected. Since the CDF also takes values between 0 and 1, we, we write f of x is equal to u. Our objective is to find the value of x. To isolate x, apply the inverse function to both sides of f of x is equal to u. Here, f inverse of f of x is equal to f inverse of f of x. This f inverse and f can be neutralized. The f inverse u is equal to x. So x is equal to f inverse u. We can obtain f inverse u. This inverse transform method is the simulated random observation is obtained by x is equal to f inverse u. U is uniformly distributed between 0 and 1. This formula converts a uniform random number into a random variable having the required probability distribution. Here our goal is generate random observations from any continuous probability distribution using uniformly distributed random numbers. Here first step is generate a random number between 0 and 1. Write the cumulative distribution function of f of x CDF. Equate the CDF to the uniform random number f of x is equal to u. Solve for x implies x is equal to f inverse u, then obtain value. The obtained value is one simulated observation. Repeat these 5 steps many times to generate thousands or millions of observations from the required probability distribution. The real life observation is many events in pharmaceutical sciences are measured by time until an event occurs, time until a tablet completely dissolves in the stomach, time until a medicine loses its potency, time between two patients arriving at a pharmacy, time until a pharmaceutical medicine fails, time until a vaccine loses its effectiveness. So, all these waiting times are commonly modeled using the exponential distribution. Here, exponential distribution is used whenever we are interested in the waiting time until the first occurrence of an event. Here, the definition of exponential distribution is it is a continuous probability distribution that describes the waiting time until the first occurrence of an event. Here, the probability density function PDF is given by f of x is equal to lambda e power minus lambda x. Here, lambda is the parameter and x is the random variable, continuous random variable. The range of x is greater than 0 and the range of parameter lambda is greater than or equal to 0. Here x is the waiting time, lambda is the rate parameter and it is non-negative. Examples of waiting time is tablet dissolution as we discussed earlier, drug degradation, patient arrival, machine failure. Here this is the graph of, this is the values of x and this is the values of f of x. This curve of the f of x is equal to lambda e power minus lambda x. The probability is highest near x is equal to 0. Here x is equal to 0, the probability f of x is high, decreases exponentially as time decreases. Here x is the waiting time. If the waiting time decreases exponentially as time increases. Hence, shorter waiting times are more common than longer waiting times. Here, what does the parameter lambda represent? We already discussed it is a rate parameter. It determines how quickly the event occurs. For the exponential distribution f of x is equal to lambda e power minus lambda x, if our interpretation is large lambda is the higher rate, event occurs quickly, short waiting time. Small lambda indicates low rate, event occurs slowly, long waiting time. Here, if the lambda is 0.5, the waiting time is decreases. Lambda 2, it is increases. The pharmacy interpretation is a tablet with a larger lambda dissolves more rapidly. A tablet with a smaller lambda dissolves more slowly. Thus, lambda controls the speed of the process. So, recall the probability density function of exponential distribution. It is f of x is equal to lambda e power minus lambda x. Our simulation algorithm requires CDF. So, we need to find cumulative distribution function or simply distribution function capital F of x of exponential distribution. By the definition of distribution function, f of x is equal to probability of x less than or equal to x for a continuous random variable. F of x is equal to minus infinity to x. The range is up to x only. F of t dt, where f of t is equal to 0 for t less than 0. We obtain f of x is equal to 0 to x lambda e power minus lambda t dt. Here, this is the distribution function, cumulative distribution function f of x, and the cumulative distribution function represents the total probability accumulated from 0 to x. So, starting with the f of x 0 to x lambda e power minus lambda t dt, simply by integrating it, lambda constant comes out, e power minus lambda t by lambda minus comes here, this lambda comes here, lambda gets cancelled, and e power minus of e power minus lambda t 0 to x. We by applying the limits e power upper limit minus lambda x minus lower limit e power 0. Here, in place of t, we need to substitute x here. In place of t, we need to substitute 0. 0 into minus lambda becomes 0. Here, since e power minus lambda, e power 0 is equal to 1, this becomes 1, minus of minus plus 1, 1 minus e power minus lambda x. So, our CDF of exponential distribution is 1 minus e power minus lambda x. This is the function required for simulation. The CDF is given by f of x is equal to 1 minus e power minus lambda x. According to the inverse transform method, f of x is equal to u. U is uniformly distributed between the range 0 and 1. Therefore, we must equate this f of x to u. Then e power minus lambda x is equal to 1 minus u. Taking natural logarithms on both sides, minus lambda x comes here equal to natural logarithm ln into 1 minus u. We know we want x is equal to this x is equal to 1 by lambda into ln 1 minus u. Since u is uniformly distributed between 0 to 1 and the random variable 1 minus u is also uniformly distributed over the interval 0 and 1. So, we can simply replace 1 minus u with u, and therefore instead of 1 minus u we can simply substitute u. Therefore, x is equal to minus 1 by lambda ln u. This is the formula. This is the key formula for finding the different x values for different u values. Generate u uniform 0 to 1. Compute x is equal to minus 1 by lambda ln u. The value of x is the one simulated exponential observation. The problem is, let us look at an example. We can understand the total concept by an example. The resolution time in minutes of a tablet follows an exponential distribution with the rate parameter lambda is equal to 0.5. Using the inverse transform method, x is equal to minus 1 by lambda ln of u. Here, the simulate the dissolution times corresponding to the following uniform random numbers. These uniform random numbers are randomly selected or a computer generated random numbers. Here find the simulated resolution time for each tablet. These are the different times random numbers. By using these numbers, we can generate 5 different resolution times. Here for 0.90, simply substitute in place of u 0.90 2 into natural logarithm of 0.90. The required time is in minutes 0.21, approximately this is equal to 0.211. Similarly, for the random number 0.10, it is 4.0605. So these are the simulated times by using the random numbers, by using different random numbers. In this manner, we can generate millions of random numbers, and we can easily identify the simulated time. Smaller uniform numbers generated larger waiting times. Here, what we achieved through this simulation is this is a virtual experiment. Instead of performing a real laboratory experiment, we generated virtual dissolution time using random numbers and probability theory. First, generate a uniform random number, apply simulation formula, obtain one virtual dissolution time, repeat thousands of times, analyze the simulated data. This is the procedure of simulation of random numbers in pharmaceutical companies. Simulation enables us to study the behavior of millions of virtual tablets, virtual patients, or medicines without conducting millions of costly laboratory experiments. Here, our complete journey is identify the probability distribution, generate a uniform random number, write the CD of capital F of x, apply the inverse transformation method, that is f of x is equal to u, find x is equal to f inverse u, and this is the real pharmacy problem. Random uniform number, simulation formula, virtual tablets, decision making. Here we are already discussed. This is very much useful in tablet dissolution, drug degradation, clinical trials, vaccine stability, patient arrival analysis, quality control. Our key takeaway is simulation transforms uniform random numbers into realistic observations from any probability distribution, allowing pharmaceutical scientists to perform virtual experiments before conducting costly laboratory studies. Here, the students are getting these types of problems given the cumulative distribution function. This is the cumulative distribution function. In case of 0, the range of x is -1. In case capital F of x is equal to, this is CDF, that is distribution function. 1 by 2 minus x square by 2. The range of x is here -1 to here, look here, -1 to 0, and 0 to 1 greater than or equal to 0. If x is greater than or equal to 1, f of x is equal to 1. If x is less than 1, capital F of x is equal to 0. Find f of minus 1.5. Simply substitute in place of x minus 1.5. It is less than -1, so it is equal to 0. Use the first part of CDF, it is 0. Simply find f of minus 0.6. Since -1 less than or equal to 0.6 less than or equal to 1, f of x is equal to 1 by 2 minus x square by 2. Therefore, substitute 0.6 in place of x. We can get f of minus 0.6 is equal to 0.32. Similarly, find f of 0.4. Since it is between 0 and 1, in case of 0 and 1, this is 1 by 2 plus x square by 2. Use this PDF f of x. Simply substitute in place of x 0.4, it is 0.58. Find f of 1.3. Since it is greater than 1, f of x is equal to 1. Given the cumulative distribution function f of x, we can find f of -2. Here it is less than -1, so it is equal to 0. Find f of -1, it is equal to 0. Find f of minus 0.8, it is equal to 1.8. Use the cumulative distribution function. For f of minus 0.5, it is 0.375. F of 0, the range is 0 to 1. So 1 by 2 plus x square by 2. In place of x, we have 0. So it is simply 1 by 2, that is 0.5. For f of 0.4, it is 0.58. F of 0.8, it is 0.82. F of 1, it is greater than or equal to 1. We need to use f of 1 is equal to 1. F of 2, it is 1. So if probability less than or equal to 0.6, this is f of 0. Minus 0.6. Simply substitute in the formula the range. This is 0.32. This is for x less than or equal to 0.7, it is 0.745. Simply substitute, you can get, you can solve any number of problems. Here probability of minus 0.5 less than or equal to x less than or equal to 0.5 is f of x minus f of 0.5. This is the range. F of b minus f of a. This is b, this is a. So this is equal to 0.25. Simply substitute the formulae, we can solve any number of problems in this type. So I wish you all the best. Thank you.